Hey folks, today I want to talk about formal verification in Info. So this is a topic that is getting more and more traction because with the arrival of very strong AI models, we've seen a lot of systems being attacked and a lot of vulnerabilities that are very old and yet were not found before. Suddenly the AI can surface them, and sometimes they are very serious. So for a system like Zcash, who is very complex and also uses advanced mathematics and algorithms, it's a bit scary to have no full confidence that everything works is mathematically sound, and also that implementation is correct. So what's formal verification and where can it help? So essentially here, what we are doing is that we're taking code and algorithm programs, functions, and we want to mathematically prove that there's no bugs, there's no corner case where the functions will misbehave or there's exploit possible. Um, so one thing I need to be clear about is that it's very difficult to fully verify every aspect of a program. Um, and because as will see later, the formalism is fairly verbose and complex, and there are some things that simply don't translate well, such as side effects and asynchronicity. And so we have to make some assumption that we are modeling we create a model of the code, but we are not 100% covering all the aspects. But yet, this is very useful because even in the PCs that are supposedly simpler, there are possible bugs, especially around the corner cases. The frame is off by one, or the edge case that when the list is empty or when the list is full, or things like that. So this is very useful still. Um, and this gives us a confidence that when we have a complex algorithm, such as the one that we're going to use for, well, it's not super complex, but this is not simple. The one that we're going to present now, the formal verification will check that the assumptions that we are making are actually they hold throughout the code. So the example I'm going to use is the code, the program we're working on for the Zcash deprecation called Zaino, which is a replacement for LiWalletD. So let me give you a short recap on what Zaino does and where it fits the full picture of the Zcash ecosystem. So in Zcash, we have a blockchain that holds the shielded transactions. Sorry, which means that transactions are encrypted, and therefore only the sender and the recipients are able to see the details of the transaction. So this has obvious very good privacy advantages, but it also means that for this to work, as a coin holder, as a person that has a wallet, you cannot rely on some third party analyzing the transactions for you, the blockchain for you, and providing you with direct pointers to your transactions and your balance, because that will obviously defeat the purpose of having privacy. Therefore, in the general case, the idea is that you are in charge of reading the blockchain and decoding and identifying your transactions and maintaining your wallet information. For a blockchain that has all the transactions for everyone, your transactions will be a very small fraction of what's out there. So less than 1 million is going to be yours. And well, not many 1 million, but less than 100,000 of these transactions will be yours. And that means that if you are to scan the entire blockchain, which is now 250, something like 250 gigabytes, this would take a long time. So the Zaino, where Zaino helps is it will trim the blockchain. It will connect to a node that has all the blockchain data, but it will do some anonymous or some pre-processing, which doesn't require you to provide any data. So the pre-processing and the filtering that Zaino does is the same for everyone. It basically trims away things like the zero knowledge proofs, the memos and information that you don't necessarily you don't need in order to identify your transactions. So that cuts down the size of the data that you would have to process from 250 gigabyte to about, let's say, 10 gigabytes, something like that, or maybe like 20 gigabyte. So a factor of 10. So that's very useful if you are running a wallet on a mobile device, for instance. It's still a lot, but it's still a tenth of what it used to be. And in order to do that, it creates internally its own index. Well, I call it index, but it's not really indexing per se, because it's not like you can jump onto a particular transaction, or you can jump to a transaction, but you will know that that transaction is yours. It's tier index in the sense that we're gonna have blocks in there, we're gonna have payload. This is structured pretty much the same way as the original blockchain, except that it has much less data. So some fields have been trimmed. So we still call it index, and the process is still called indexing, but it's not exactly like a database index per se. All right, this is what it does, and then the main API that you need from so this guy, the Zaino, sits between Zebra, which is a full node server, meaning that it talks to other Zebra instances and it synchronizes the blockchain, the full blockchain, and it sits between Zebra and the wallet clients such as Zodo, Zico, Zingo, so all these guys who are called light wallets because they don't connect to the full node. Right? They connect to that. You can consider that as a proxy between the light wallet and the full blockchain. So the only really big API, the primary role of Zaino is to serve a range of blocks. So let's say that your wallet is not synchronized or getting to synchronize. The wallet would say, hey, what's the current tip of the blockchain? We say like 3.3 million, something like that. And then we say, okay, well, I only have up to 1 million. So please give me all the blocks between 1 million and 3.3 million. And that's 2.3 million blocks, of course, right? And that's quite a lot. So while you synchronize, while you get those 2 million blocks, it's quite possible quite likely that the blockchain will change. New blocks will be added. Potentially, there could even be a reorganization. So even though it may happen from the client perspective, from the wallet perspective, the wallet app perspective, it still wants to see these 2.3 million blocks continuous. Right? At the moment it made the query, and it said I want blocks from A to B, it expects to receive a chain of blocks that are properly linked. Right? And that means that by the time it reaches the end, the block B, that block B may not be the last block anymore. The tip may have moved, or may be not even part of the best blockchain anymore. B could be a fork that is no longer the main fork. Right? So that's a real possibility that we have to consider, and we have to articulate our software around these constraints. So that's why the synchronization and the code that we're going to talk about here is a bit tricky. And also we want to do that with a lot of with good performance because because we're talking about 2 million blocks here. We can't say that if we have 1,000 clients connecting at the same time, we cannot say that the clients will have to wait between each other, because one client can ask for like 2 million blocks, and that would take that would probably take maybe 10 minutes to get. So we expect some level of concurrency and fairness between the clients. All right, so that's the goal of Zaino. And let me recap. The goal of Zaino is to capture blocks from the upstream, then extract, trim it down to the compact form, and then put into an index, so that when client comes and requests blocks from a range, it can serve this range in a way that behaves like a snapshot. So at the time the request came, we are logically taking a snapshot of the range, and even if that range changes during the scan, the retrieval, it remains the chain that we send to the client. All right. So how do we design this? So this is the new design. There's an existing design I will not cover, but this is the design that's gonna added as a PR. So the design here is actually very similar to what we have before. There's a major assumption that is enforced by Zebra, is that if there's a reorg, meaning that if blocks that are part of the best chain are evicted, are no longer best, this can happen, for example, if you have two miners that as they work in decentralized fashion. If two miners propose or found a block at the same height, but then one block is extended and the other one is not. So the proof of work algorithm or rule is that the chain that has the highest proof of work is the main chain, is a valid chain. And this is all taken care of by Zebra. It's not something that we have to care to handle. But what Zebra would do is it would automatically switch between forks in order to follow the one that has the highest proof of work. So for us, it's for Zaino, it's completely opaque. It's something that we don't know. We just know that if we query the upstream Zebra, we only have two APIs. Basically, we can ask for where's the tip, so it returns a height and a hash. And we can also ask for, hey, what's the block on your base chain at a given height? And because of reorg, we have to be aware that if we ask for the same height, we may get a different block between calls if reorg happened. So this is the whole extent of the contract we have between Zaino and Zebra. The other contract is we have between Zaino and the client is give me a range A to B, and we just serve compact blocks. Okay, so the constraint I was talking about is that the reorg from a blockchain cannot be longer than a certain constant, which is 100. Which means that, for example, if we reach a height of 1,000, we only allowed to roll back up to 900. So we don't have to, even if the system rolls back in multiple steps. So for example, it went from 1,000 to 950, and then it went to 952, and then it rolls back to 902, and then that's still okay. But now if it rolls back to 890, then that's not okay. So essentially what you have is that it behaves like a range, a moving range. As new blocks come and the tip moves, the range goes forward. So at 1000, the range is of valid reorgs is from 900 to 1000. But if you then receive more blocks and you reach, for example, 1010, then you are only allowed to rewind all the way back to 910. Right? So whether it's one go or multiple go, you only have allowed to stay in that range of 100 blocks from the maximum block that you have, maximum height that you have reached. And that also means that when we are at a given height, all the blocks are from 0 to height minus 100. So everything that is from genesis to the beginning of that moving window can no longer change because we're not allowed to roll back to that point. So these blocks from the range 0 to h minus 100 is going to considered safe. So this is going to be our safe zone. And then we have from h minus 100 to, let's call it 100d, h minus d to h, blocks are potentially may change if we have a reorg. And of course, this range moves forward as we get more blocks. So we in our app, in Zaino, we're going to make the distinction between these two zones because having H blocks in memory is not practical, it's not feasible. Well, it's feasible, but you would need a lot of resources. That means that currently H is about 3.3 million and D is just 100. So most of the blockchain is safe now. And safe means that we can write to a database. The idea of this design is that we have a two-tier approach where the majority of blocks are going to be in the safe zone. And then we have a bunch of blocks, like about 100, that are going to be only in memory because there's a potential reorg that will change them. And that little part that we have at the end, sometimes they call the non-finalized zone, it's not going to be written to disk, which means that when the app restarts, if you restart the app, we're going to have to recover that zone. And it's just 100 blocks, so we don't really, it's not a very big deal to go to Zebra and request 100 blocks. It's a big deal not to have to request 3 million blocks, right? So the important thing for the index is the safe zone of 3 million blocks that we have written to disk. And the logic of this stuff is that at any point, if we consider the chain from Zeno's perspective, it begins from genesis or whatever height you have decided to begin with in Zeno. Actually it's a configurable setting. You don't have to start at genesis. You could start, for example, at sapling activation because Zeno is mostly used for shielded transactions, and there are no shielded transactions in the modern pool. Well, there's in Sprout, but there are no more transactions in sapling, orchard before activation. 419,200. So you can save some storage by skipping that zone, but we're only talking about 400,000 blocks in the big picture of 3 million. That's not such a big deal, since most of these blocks will be empty anyways. Well, they're empty of shielded transactions, so the compact version will be really empty. It's just going to have the header, so you are storing a few bytes there. What I'm trying to say is that what I was saying is that you have the logical model is that from the beginning of the blockchain 0 to the end, to the tip, the current tip, this should logically form a continuous chain, and we know that but it's chain when the block has a previous hash. So previous hash is a field inside the block header that is the same as the block before it. So same as the hash of the block before it. So the chain is chained backwards. The last block, the tip, is chained to the one before, which is chained to the one before, and you continue that for 3 million blocks, and you reach height 0, which is a hard-coded starting block. So that one is frozen and defined in Zcash software. That's called a Genesis block. But in practice, in our implementation, the store is actually two pieces. We have the freezer that goes from block 0 to CS minus 1. Then we have the in-memory chain that goes from CS to CT minus 1. And then we have blocks that are not there yet. So what do these values mean? So the range here is given inclusive. So it's usually better to work, easier mathematically to work with open ranges on one side. Because if you have an open range 0 to CS, so close on 0, inclusive on 0, and open on the end, then you can say that the length of that range is simply n minus start. For documentation, all this stuff was actually generated by AI based on the code on design I made. It found it easier to do inclusive, so it's going to say that it's from 0 to CS minus 1. And CS is basically it stands for chain start. So the in-memory fragment that we keep in for as a working zone, well, we call this the chain, right? And then that is really just a fragment of the chain. And then we have the freezer, which contains the stuff that we have written to LMDB. LMDB is our database. It's a database that is very efficient for concurrent reads. If you have occasional writers and a lot of readers, it has a lot of very good concurrency. It's pretty low level, so it only does byte to byte. It's perfect for us because a block for us is essentially opaque. It has the only thing we need to know is that it has a hash and it has a back pointer. So it has a previous hash. The rest we don't really care for the index, of course. Then the zone that starts from CS goes from CS to CT. CT stands for the chain tip. Chain tip corresponds to what Zaino think the tip of the blockchain is. It may not be the best tip anymore because obviously we may not be synchronized with the remote, but this is our best knowledge of the blockchain. So from 0 to CT, again 0 inclusive and CT exclusive, we have all these blocks in our chain. So a few more conditions. The first condition is that this memory, the in-memory part, let me get you something that looks a bit better. This in-memory part of length CT minus CS, we limit it to D because we only need D blocks here in order to support a reorg of level D minus 1. So here we put it as 101 because we are saying that the reorg, maximum reorg is from the Zebra is 100. It's not super important because it's not like 100 is a magical number. We just decided 100 is fair, it's safe enough. It could be really like 99 or 101. Already, if you have a reorg of more than 80 blocks, you are probably in trouble. But what it means here is that to be exact, because we don't want to have issues with counting off by one, so things like that. We are saying that if the reorg is one block, so one level reorg, means that the latest block, the tip, is replaced. So normally you would add new blocks as they come to the tip, so they will be appended. But we are saying that if you have a one level reorg, the current tip is replaced. And some people would call it a zero block reorg. So the terminology is not 100% fixed. Since the 100 is a fairly arbitrary value, I have decided to call this a one block reorg. So if you have a one block reorg, then it means that in order to detect that your previous node has that you have changed, but your anchor, so the fork that you are making has one level, you need two blocks. But you need obviously the tip, and you need the parent of the tip. So the new block would come and see, oh, I'm not the same as the tip. Where should I be inserted? Then it needs to look at the parent of the current tip. It will see that it's the same, and then say, okay, I would attach to the parent of the current tip. So that means that we are now looking at two blocks, the tip and tip minus one. So that's why the chain, in order to support a D-level reorg, so in that case it was a one-level reorg, it needs two blocks, the current and the one before. So in general, if you want to support a max org def reorg of X, you will need to have X plus one blocks in the chain. So we define that guy to be 101. Then there's explanation why this is 101. Right? That's exactly what I said, but it's a bit more of a compact here. So we have these guys, and we have operations that support the update of this structure based on what we see and what we have, right? What we see from upstream and what we have currently. And I'm going to describe the very low-level operations. So before we go to the low-level operations, we need to do. I want to say to discuss what we want to keep true for this data structure. So we already said that this data structure has two parts, and these two parts glued together, they represent the blockchain. So we need that the freezer is a chain. So chain means that next points to previous. So we already need that guy, right? So if the freezer is disconnected, then something is very wrong. We also need the chain to be a chain. But we also need to have the freezer and the chain connect at the seam, at the level of CS. Right? And that can be easily expressed in formally by saying that freezer plus plus appended concatenated with CS form a chain. So I don't know if it's there, but it should be there somewhere as an invariant. This is it's going to be in the lean document. Right. So we have that as the main condition. Yeah, it should always be true. Otherwise, our data structure is corrupted. And we also have a few observations based on the fact that the definition of CS and CT. So if CS and CT are the same, then it means that our memory chain is empty. That's pretty obvious because the chain goes from CS to CT minus 1. So if CS and CT are the same, this is an empty set. The chain is empty. Then we also say that CS, by definition, is also the size of the freezer. The freezer has always only one block per height because it only stores the base chain, and the base chain has only one height per block, of course. Then if the CS is 0, then again, that's by the same logic, it means that the freezer is empty, right? And you have this definition here as invariant here. So nothing very peculiar to that. Then we have operations that are going to change this data structure. And we choose these operations to be fairly low level, because then we can prove that these operations in isolation, we preserve the invariance. We preserve this condition, plus the one that is not mentioned here, that blocks freezer plus chain forms a valid chain. So we want to define these low-level operations very simply, so that we can verify or provide proofs that they are correct and don't break the invariance. And then we are going to compose them into something more useful when we do the full synchronization algorithm. So let's start with the small stuff, right? The simple stuff. One is the first simple stuff as a primitive is writing blocks to LMDB. So that's going to happen if when we are evicting blocks from the chain, because we are saying that the chain has a maximum size of D. So if future blocks come in, they will extend that chain, and then when it overflows, we can safely write the head, the prefix of the chain into our freezer in order to free up some memory. So without that logic, then obviously the freezer will remain empty. So when we write blocks to LMDB, we are giving a series of blocks that have a hash and a height. We write them to the freezer. And we also want to put something in the freezer that stores the number of elements we have. This allows us to recover CS faster than if we had to scan the freezer to count how many records are in there. So which just a performance optimization. You could do a freezer where on startup the CS is derived from counting all the records we have. And it's also possible that actually LMDB is capable of doing that efficiently. But I'm not sure. I don't think so actually. So yeah, I think it's fairly fast. It's not like super fast. It's not all one. I think it has to scan some stuff. So in order to make this a little bit more performant, we also store the count of records as a separate record. Right? And if the store is empty, then that value is not going to be there because it's also a record. But we on recovery will say that this value is zero, store is empty. Right, so that's our first stuff. The second simple primitive we have is the one where we have something in the chain and we want to save that chain to the freezer. So in that case, what we have is we write everything from, what we do is we write everything from the chain to the freezer. Then increment, of course, in the process, the count that the freezer contains. And then we bump up the CS. So now that this guy has been written, CS will progress, will jump forward of the length of the chain. And that means that CS will reach CT, because CT, as you remember, CT is always equal to CS plus length. So after that bump forward, CT is going to become CS, and then the chain is empty. Right, so really, we only have to do this. These two guys are the consequence of, well, we have to delete the chain, right? But CT is going to become equal to CS by construction, by definition. So the post condition is that this guy is equal to CS is equal to CT, and all the blocks are in the freezer, and our chain is empty. Right. So that's called flushing the chain. Then we have direct append to the freezer. So this is used when we are very far away from the tip and we want to quickly ingest blocks. So for example, you start and you are at block 0 because you have nothing. And now you see that the tip is at 3 million. So you have a long time before you're gonna get close to the active range, to the 3 million range, 3.3 million range. And all the blocks that you're gonna get in between from zero are immutable at this point. They are so far from the tip that there's absolutely no way that you can reorg that to them. So instead of going through the process of inserting them into the memory chain and then having them trickle down into the freezer, what we can do is directly write it to the freezer, right? So in order to write to the freezer and not break the invariant that freezer plus chain forms a chain, we have to make sure that the chain is empty. So this is our precondition. We must have an empty chain in order to bypass the chain. If that's not the case, then we can always make the chain empty by first calling flush chain to LMDB. So if we call that guy, chain will be empty, and then we can append to freezer. So what are the invariants? We must have a chain that is empty. Then we can write the blocks to LMDB, and then the blocks that we write, of course, they have to be consecutive. We have to make sure that these blocks, they form a chain with the stuff that we had before. But if it's good, then we can bump up the start offset, the start height of the memory by that number of blocks, right? That will make sure that these invariants here are preserved. CS is equal to the length of the freezer. Since we have added records to the freezer, we have to count for these records. Right, so also pretty simple. And doing this append does not change the chain, so the chain remains empty. Therefore, we have also to update CT to be equal to CS. So the chain tip advances as well. Then this is now the biggest function we have. The biggest function we have is this append to chain. Right? Append to chain is the one where we are now adding blocks to the in-memory structure to the chain. Before we were adding to the freezer, and we know that these are immutable, so that was not very risky. We just write directly to the freezer. Now, if we want to update the chain, this is a bit more tricky because we may not, it's possible that we are not appending to the end of the chain. So appending to the end of the chain means that we are extending the chain with more blocks coming. And that's the regular situation when simply there's no collision between miners and the chain simply extends with having one block added. But that's not always the case, and we have to handle this situation. And we also have to handle the situation where we're adding more than one block. So let's say that you went off, Zaino went offline, and then 10 blocks were mined before Zaino goes back online. So when we create the tip, we will see that the tip is farther from us by 10 blocks. So we are not appending just one block, we are appending a fragment. In this case, a fragment denotes any series of blocks that are properly chained together, but they don't go all the way to genesis. Right? So it's just a portion of the blockchain. And the other condition is that fragment may not be extending the tip. Right? So that's why we also have this parameter called the anchor height, which is the height of the block that is before the fragment. So if we're extending the tip, that anchor height will simply be the tip height. But if we are, for example, have a reorg of one block, this will be tip minus one. So we also have some conditions. First condition is that the fragment that we're adding is not longer than D blocks. And you may ask yourself, wow, this is that sounds incorrect, because what if we are far behind? We went offline for a year, So we have some data. We have it is not in the scenario where we start from scratch. So we have some data, but we went offline for a significant amount of time, and now the tip is far from us. It's longer than D. Or another case would be that we start synchronizing, but we stop in the middle. Right? We turn off the computer, we come back, and we have processed 1 million blocks, but we still have 2 million blocks to go. So clearly, the fragment that we would get is longer than 2 million, longer than D because it's 2 million. And the reason why we can assert that that's not the case is because in our synchronization logic, we're gonna have another path before this, which will do a fast forward. This is only going to be called with the condition that the fragment is lower than D. And this is where the verification kicks in. Because since we are getting this as an assumption, this assumption must hold true. So we can hold it true as by putting an assert in the code and say that if it ever happens, we panic. But this is not very nice, right? This is something that could blow up during production. And what we have with verification, formal verification, is the fact that if we have coded the logic, if we have designed the logic properly, this is impossible. This will not happen because some other case would have handled it. And before, without verification, capturing this kind of interconnection between functions is extremely hard. You cannot have your compiler, or it's very hard at least to have your compiler check for this kind of compile time assumptions, invariants, because they involve the behavior of different functions. And this is when the formal verification is bringing a lot of value, because we are going to be able to capture this as actually equations and proofs of statements, of properties, and then have the Lean4 program verify that this assumption here is actually very provable. It's never gonna assert. It's never gonna panic. Right. So that's gonna be done later. Right. But for now, we are saying that the fragment that we're adding has a length that is lower than D. And also we are also saying that the anchor height here is therefore going to be in the range. Right? So this is kind of obvious because we are saying that when we find the anchor, because the reorg is less than D block, it cannot go higher up than CS. So the anchor height is somewhere between CS and CT. This is not something that we can prove, right? This is coming from the fact that we do not allow, Zebra does not allow a reorg that is deeper than D blocks. And therefore, when we translate that into mathematical constraints based on our system design, it means that the anchor, the place where the fragment gets inserted, has to come inside that range. And that's not an accident. We designed the chain to have exactly the number of blocks that are required for a reorg of D depth, of that depth, maximum depth. So we have also that. And then the logic in that case, it would be that we truncate the chain at that anchor height, meaning that now that we have reorg, the part of the chain that starts from anchor height +1 to the remaining is no longer the best part. So this is going to be removed from the chain, and then we append the fragment instead. Right? So again, this guy here is going to be verified in the sense that the question you could ask is, okay, we are truncating the chain and we are appending something. Is it going to still be true that we are not going over D, and what is the result of this happening on chain? Is it possible that we go below 0? Is it possible that we're happening too much? We have a memory constraint on that chain. We don't want to be appending, for example, 3 million blocks here. Right? So this can be expressed in both in pseudocode and in lean. So for now, pseudocode. So we express this as because we added we did this transformation. We also pushing. We have to re-update the tip. So the tip is always CS plus the chain length. So this is just by definition of the tip. CS is the start of the chain, and CT is the end of the chain. So the end of the chain is the chain start plus the length, of course. Right? But here's the new the new condition. We are saying that after this operation, the length of the chain is at most 2 times D. Right? That may sound very simple actually, and I think that for this kind of simple system, you can prove it. You don't really need to do all of this. Right? You can prove it just by the fact that it's not very complicated. And the proof here is that we know that before we enter this, the invariant was that the chain was at most D blocks. Therefore, and then we added at most D blocks, right? So if this guy was not truncating anything, this is the worst case. We don't truncate anything, and we just append the fragment. So we are appending at most D blocks on a chain that has D blocks at most. So the result is that our chain is now at most 2 D blocks, right? So this is really straightforward if you think about it. But the beauty of the lean, the formal model, is that this kind of computation can actually be done by the lean 4 compiler. Right? This can be expressed as code, and this can be proven without me like making some reasoning, verbal reasoning. Then we have the final stuff, which is the final low-level operation, which is trimming trimming the chain. So after this operation, the append, we know that we may be up to 2 D blocks of length in the chain. So we want to trim it back to D. Right? So we are saying that if the length is now greater than D, then we are doing this spear to disk, spear to freezer. We take the difference, so the overflow, and then we write the head of the chain to the database. So we flush to disk that portion, and then we shift the chain by C blocks. So by shifting by C blocks, now we have a chain that is exactly D blocks long. So we just have also to update the start offset. And this does not change the tip. Right? We are just saying that we are essentially saying that CSCT now is this piece now is too long. So we are moving CS closer to CT, so that we have now back to D in between, and the part that is between CS and the new CS is written to disk. So the freezer has extended. As a note, whenever you write something to LMDB, you go through this function here. So this also assumes that you have updated the count on that is stored in the freezer. So that's why this function was called out. You don't just like write to LMDB. So with these functions in hand, now we can go over the synchronization algorithm. And this is where we put all this stuff together. This is a 6-step algorithm. So let's go through these steps. The first one is we ask the remote for the tip. And asking the remote for the tip gives us two things. It gives us the remote hash and the remote tip, just the height. So now after that, we compute the gap, right? The gap is how many blocks are between the remote tip, the real tip, and the tip that we have. So RT minus CT. And that is a signed value, meaning that it could be negative. It's negative if, for example, there was a reorg, and we are now ahead of the remote tip. We are, let's say, at 1,000, but there was a 10 block reorg, and the remote now is at 990. So we have to account for this because this has happened. Incidentally, this is actually a bug that Zaino has now. If the remote rolls back, then the current algorithm is actually storing. It enters an infinite loop. So, and one of the beauty of this formal verification is that this would be caught by the system. All right. So the gap now is a signed value, and in normal cases, it's going to be greater or equal to 0. Right? Now, if it's greater than d, it means that we're actually far behind, while far being greater than d. So it means that if we fill the gap, these blocks that we're going to fill are going to go straight to LMDB, to the database. So what we do now is we want to do a fast forward. We want to read straight from Zebra and go to the fast path where we dump things into LMDB. So that would cover the case where we do the initial sync, and also the case where we do a long catch-up. Long catch-up meaning we were offline for longer than D blocks. So what do? We call the flush chain to DB, which is the function up there, and that clears the chain. So that flush is all the blocks that we have so far in our staging area. Then we can do this loop, right, where we fetch from the remote and we write directly to the database. This one is written a little bit verbose, because we could say we fetch the gap, we fetch the RT minus D. But this is written as a loop because we wanted to capture the fact that if it's 3 million blocks that you are behind, we are not going to ask for 3 million blocks from Zebra. What we're going to do is we batch the fetch. We go, for example, 10,000 blocks at a time, whatever. I don't remember actually what batch is. But we retrieve some amount of blocks in multiple threads, and then we write these as one transaction to LMDB. Then we commit, and we repeat. Right. So the idea here is that when we do that, we can make multiple requests to Zebra to fetch a lot of blocks in parallel. And we also want to write to the database and update the count, so that if you abort and restart the process, if we start Zaino, you're gonna come back here, right? You're gonna get the gap, but CT would have been updated, right? CT after recovery is gonna be equal to the freezer count. So the progress has been recorded, and you're not going to restart from running from zero. So this also basically handles the case where you do a partial sync and then you restart. So after this guy, after step number 3, now you have essentially closed the gap between CT and RT, and the difference between them is going to be at most D, right? Because now the gap it has closed by that much, and that means that you can do the slow sync. So the algorithm of the slow sync is described elsewhere, but essentially what it does is it retrieves the block from the zebra, and it walks it backwards. It will take that guy, and then if that guy's block is not in our chain, it will ask for the parent, and then check that the parent is still linked, because there could be a reorg in between, and see if that parent is in the chain, and repeat that process until we run out of steps, because we are committed to do that for only a fuel amount, so D blocks. And if we run out of fuel, it means that that chain that we get from zebra is longer than D blocks. So that's the reorg that is too long. We are bound to hit an element of our chain, a common ancestor, before we run out of fuel. Once this happens, we have the anchor height and we have the fragment. Right? So then we can call the append to chain function that we have described before with the anchor, which is the parent, basically the common ancestor between the fragment and the new chain and the old chain. And this guy will update our chain with the new best fork. And this also handles a case where we're simply extending, because if you are simply extending the chain, then the parent will be exactly the tip. So we have to walk just one block, and we realize that we have already found the anchor. There's one special case here, if you notice this. It's just the optimization when we happen to be already synced. If we're already synced and we request a block from the server, or the block that we receive is going to anchor exactly on the parent, because we are the same. So in that case, if we recognize that the fragment has only one block, and it happens that that block is the same as our current chain tip, then we don't do anything. We don't have to truncate by one and then append. Technically, we could, because this would be a new operation. We are truncating by one and we're adding the same guy. So it's like removing and adding the same dude. And then updating everything. But that's pretty pointless. So there's a little bit of optimization here. I think it doesn't really make any difference because we only poll it once every 5 seconds. So this should take like a few nanoseconds to do. It may not even be worth to implement this optimization. Then after that, we know that the chain could be longer than D, so we call the trim D, trim chain. Trim chain will make sure that after that step, we are back to lower than D. So then at the end of this sync, we are back to the starting point invariance. Okay, and then there is some explanation about what I just said here. So why we always do a slow sync? We always do a slow sync because it's possible that gap equals 0 does not necessarily mean that we have no thing to do. If we, for example, said, and I think that was a bug in Zaino before. If we say that, for example, if the gap is lower than 0 or equals 0, it means that we are synced. That is not true, because it could be that the remote is now shorter than us and has actually switched to another chain. Or it could be that the remote is the same length as us. We are or still aligned at the same height, but we are on a different chain. So just comparing chain height is not enough to be synced. So we always do this slow sync because the slow sync actually compares the hashes. And if we are in a case where gap is negative, then all we do here is that we take the block that we got from the tip from the remote, and we compare with our ancestor in the chain, and we will see that that guy connects to some height above the tip, our tip. So that the current chain fragment that we have from the anchor point to our current tip is going to be discarded, and it doesn't care whether we are discarding one block or we're discarding 10 blocks. So we just replacing the segment from the old chain with the new chain, and that handles any kind of level reorgs. It could be a reorg that extends on the branch, compresses on the reduces on the branch. It doesn't really matter. This is all handled here. Therefore, this code here is going to be called every time we do a sync. This guy here may not happen because in normal situation the gap is not very large. But this one here is where we handle chain extension and chain reorg. So that has to be done. And also the trimming is not always done. So in practice, once you reach stable behavior, stable run, you're gonna run with a chain that is fully occupied, contains all the D blocks, the latest D block, and then whenever something gets inserted, it's gonna make the chain grow larger than D. So you're gonna have to trim something. And trimming is actually natural when you think about it, because it just means that you're taking a portion of the chain and you're flushing it to the freezer. That's natural, because as more blocks come from the tail, in order to preserve the sliding window of D blocks, you're gonna have to write ahead to the database. So trim chain is called, and then this is just checking that everything goes well. So this is algorithm I explained for how to find the anchor. It's very natural. You loop through the fuel, you get the block, and you build your fragment, right? So you accumulate stuff from Zebra at height h minus 1, h minus 2, right? So every time you decrement, and you append your fragment. You also make sure that the fragment is valid. So you're checking that the fragment connects with the previous one. Okay, so this one is not really an assert. It's more like, if that's not the case, the implementation would just throw an error, and the error would propagate up, and it aborts the synchronization. So that means that at this round of sync, we saw a reorg. So we were seeing intermediate blocks as we were walking. Therefore, we are not updating anything. We are leaving the state as it is, and we're going to retry again in 5 seconds, because this is a loop on the timer. And 5 seconds later, hopefully the blockchain has stabilized, and this stuff will read from the new fork and not have a discontinuity. This is fairly rare, because it just happens that while you are fetching new blocks from Zebra, reorg happen in the middle. In normal situation, since there's a block every minute and so, you wouldn't even have this code hit, because you would have only one block in a fragment. So this really doesn't give any performance issue. Just note that this is not an assert. This is a return error. And then you check the fork. So that just means you're checking, comparing with the chain that you have, if you have reached a common ancestor. So at h-1, which is guaranteed to be in a chain. So this guy here is defensive, but the code may actually skip that, because from formal verification, we can be sure that it never hits, because the fuel is set at D, and the chain is at most D. So we are never gonna hit a point where we are running out of chain space and we are hitting to the freezer. So the common case is this one. We have found an ancestor that has the same previous hash. Therefore, we have found the fork point, the anchor. Then we return this anchor. Otherwise, we loop. Right? So really, there are two errors we can have. We can have this reorg too deep because we run out of fuel. And that's not possible really if the condition that no reorg is deeper than D. And the other stuff that happens very, very rarely is that as we are walking back the chain, the reorg happen. So we just get an error and we retry. In normal scenario, we're gonna find the ancestor, and that's the point of this function. It finds the anchor index. And that's it. Okay, so this is actually much longer than I thought, so we didn't have time to go into the formal model, but at least we have covered everything about the design and this stuff, how this stuff works. So in the next one, we can just straight jump into the Lean4 file. So I hope to see you there.